Okay, so next problem, 7.29. Is it possible for there to be points E and F on the side BC of triangle ABC such that BE equals EF equals FC and angle BAE equals EAF equals FAC? Why or why not? So that's a lot to work off of, but let's just start by making triangle ABC. And from there, seeing that we have these segments that are all the same, BE equal to EF equal to FC. So starting at B, then we have a point E, a point F, then C. So it's basically cutting BC into thirds. So let's draw some lines to those points. So what I'm going to do is label this. It's a little off from what I would like. Label this as F. Label this as E. Now, the problem is stating that all these sides are the same. So BE is the same as EF, is the same as FC. And it says that BAE, this angle here, is the same as EAF, this angle here, which is also the same as FAC, which is this angle here. Is it possible for this triangle to exist? Well, I have equal angles, which makes me think angle bisectors, which makes me think the angle bisector theorem. Now, the angle bisector theorem, I can make some ratios out of that. So, which triangle could I use to do that? Well, this big triangle ABC's, the angle A is being trisected. We have no angle trisector theorem that we talked about, so I can't use that. But what I can do is break the triangles down like this, from B to A to F. Because if I do that, and I'll shade it in blue, when I do that, I now have a nice triangle where the angle is being bisected instead of trisected. And now I can use the angle bisector theorem. So the angle bisector theorem, if I think of AE as the angle bisector, the angle bisector theorem states that AB over BE is equal to AF over EF. Okay. Well, can I get anywhere from here? Well, BE and EF are the same. So I could, instead of writing it as like BE and EF, whoops. Whatever. I'll just actually write it out. So instead of writing BE and EF, I can just call these values X. So AB over X equals AF over X. Now, if I multiply X on this side, I'll be left with AB equals, well, AF times X over X. X over X cancels out. I have AB equals AF. So over here, AB equals AF. So that's probably something I should note. AB is the same as AF. That's interesting. That means we have an isosceles triangle, which means that these two angles here and here must be the same. So let's try the same logic that we just did, but let's use another triangle, AEC. Because by using that, and I'll color that one in red, AEC, by using the same logic we just did, we can figure out even more information about this triangle using the bisector theorem that we just covered. So, applying the angle bisector theorem to triangle AEC, we have AE over EF is equal to AC over FC. And we should know FC is the same thing as X, so we can rewrite it like we did last time. We have AE over EF is X equals AC over X. And I'm not going to write out all the math, but you see it's the same thing as last time. We will get that AE is equal to AC. So AE and AC have the same lengths, which means that AEC is an isosceles triangle, which means that these two angles are the same, here and here. Well, that's pretty interesting. So now that we've proven all of that, let's clear off some of this work because we don't need it anymore. Whoops. Whoa. Alright. Let's clear off. This thing's a pain. Alright. So, hopefully we're starting to see a lot of interesting things happening in this problem. Whoa. I do not know what all that was about. Okay, so now that we have proven all of these equal lengths and stuff, do we see anything that's going to make it a problem for this triangle to exist? Well, we have a lot of the same triangles. In fact, all three of these small triangles are the same because we have side-side-side congruence. We have that triangle ABE is congruent to triangle ABE AFE, which is also congruent to triangle AFC. By side-side-side. Now if that's true, then that means the angle ABE is the same as the angle AEB. So, or I mean AEF is the same as the angle AEB. So these two angles are the same. And the angle AFC is the same as angle AFE. Well, that's interesting. So, if angle AEB is the same as AEF, and I'm just going to call these two, we'll call them Y. So these two angles have a measure of Y. Well, they're two angles on a straight line, so that means Y plus Y is 180. That means that 2Y is 180, which means that Y is 90 degrees. So these two angles are actually right angles. So these measures here are right angles. Right angle here, and even a right angle over here. Well, that's cool. But the same logic can apply with these two angles. This is, I'll call this measure of Z. And we'll do the same thing. Z plus Z is equal to 180. Which means that the same logic, Z equals 90. So we have that these angles at Z are 90 degrees as well. 90 degrees here, 90 degrees here, 90 degrees here. Now this is a very weird situation because let's just take triangle ABC, right? Triangle ABC, all the angles have to add up to 180. And if we add up all the angles, that means I know that angle at B is 90 and the angle at C is 90, so I just have plus the angle at A. Well, 90 and 90 is 180 plus the angle at A equals 180, which if I subtract 180 on both sides, that implies angle A is 0 degrees, which is not a triangle. Because if A has a angle measure of 0 degrees, that means it would be a line, just like that. There would be no angle measure at all to work with. So that can't be true. And it also implies, like, every one of these angles, it implies everything here, here, and here is 0 degrees. Which means that none of these triangles, ABE, AEF, FAC, could exist as well. So no, it is not possible for this triangle to exist. Because there's a clear contradiction in what we know about triangles and the information that we have in this problem.